So for problem number 25, we have this, what is it, cardboard? Square piece of cardboard. So just like one of the examples we did in the notes, we have a 24-inch on each side square piece of cardboard. And we're going to be cutting squares out of each corner, folding them up to make this open top box. And the open top box, just like we did in the notes, since x is the length of each of the squares out of each corner, that translates to the height of the open top box. And just again, if we take an x away from one end of this 24, take x away there, and we take an x away from the other end of this 24, and we do that for each one, for each side, right? Then what we have left in between here and here, right? So that's the same as this guy right here. That's 24 minus the 2x, right? So we do that for each one. We have 24 minus 2x, right? So we have the volume in terms of x, and the volume we know is length times width times height, and so we have, well, I put the x first, so I put the height first, height times length times width times length, if you want to say it like that, and that's fine. So we have x times 24 minus 2x times another 24 minus 2x, which we could express that as writing x times 24 minus 2x quantity squared, and that gives us the volume of the open top box in terms of x. So I'm hoping that's what they were asking for. Yeah. What is the volume if so for part B, so that's part A. For part B, what's the volume if a 3-inch square is cut out? So I'll let you do the math on that, but if now that we have our volume expressed as a function of x, we can easily find the volume if we just plug in a 3 for the x. 24 minus 2 times 3 squared, and you're eventually going to get, what is that, 972? And since we do have context, we're going to say that's square inches, okay? Oh, cubic, sorry, cubic inches, because it's volume. And then part C, what is the volume if a 10-inch square is cut out? That's the volume when x is equal to 10. So we have 10 times 24 minus 20, 2 times 10 squared. 24 minus 20 is 4. 4 squared is 16. 16 times 10 is 160. Again, that's cubic inches. And then use a graphing utility to graph A equals A of x. Let's, for part D, let's apply some logic to this, not just blindly draw a graph. Thinking about cutting a square out of each corner. We have 24 inches to work with, and so if we think about this, if we cut no squares at all, then we don't even have any volume. We just have this same cardboard. So we have to have x has to be at least 0. So x has to be greater than 0. But what does x have to be less than? So we're trying to figure this out. So thinking about the domain of this function volume, this volume function, if x is 10, then we go 10 and 10, we still have 4 more. But if out of the 24 we take 12, then we only have on the other side 12 more, and so we could take 12 and 12, and then we would have no volume either, because 12 and 12 that adds up to 24, and so the lengths of the sides would be 24 minus 24, and that'd be 0. So the lengths of each of the base sides of the base of this open top box, they would have a length of 0. So we can't go all the way to 12. We can be just shy of 12. So anyway, this just helps us with our domain, and let's take a look and see what that would look like. So if we type in the volume function, you can do this on Desmos. Type in an x, parentheses, 24 minus 2x, close parentheses, and we square that. So don't get, I almost put a cubed, but I didn't multiply all that out. But once you multiply that out, the volume would be in terms of something cubed. And if we adjust our window from 0 to 12, 12. Now the volume can't be less than 0, but it could be up to 972, so let's even put 2000 on there as a maximum so we can see it. So we can see our graph based on the given parameters, and we just draw our graph. So this is the volume graph. And we go there. That would be 12 right there, 0 there. And there we have it. That's the volume in terms of x, which is equal to x times 24 minus 2x quantity squared.